Assalamualaikum. Good morning. Okay, class. Today we continue our lesson still on ultraviolet to visible spectrometer. So you have learned last week about the differences between the bulk semiconductor and also the quantum dot semiconductor. So today we are going to learn the theory or the aspects of bulk and quantum dot semiconductor from the perspective of absorption spectrometer. So absorption spectrometer, we need to study the light that is being absorbed by the semiconductor. So both of the bulk and also quantum dot semiconductor, they behave differently. They absorb light differently. So we are going to look at the excitation of both of the type of semiconductor. The first one is the excitation of bulk semiconductor. So let us take a look at the, First, let us take a look at the band, the valence band, also the conduction band of the bulk semiconductor. So imagine that you have closely separated energy levels in the valence band and also in the conduction band of a bulk semiconductor. They are closely separated. Remember, this is the properties of bulk semiconductor. The energy levels are closely separated and they are continuous. We cannot differentiate and distinguish between the energy levels. So the conduction band is made of closely separated energy levels. The electron excitations occur from the valence band to each corresponding energy levels in the valence band. Sorry, this is not valence band, this is conduction band. Electron excitations occur from the valence band, which is the blue color, to each corresponding energy levels in the conduction band. This is typo, this is not valence band, this is conduction band. So imagine that we have source of light from the sun, for example. We have so many wide range of spectrum from the ultraviolet to near infrared, and this light being absorbed by the electrons in the valence band. So what happens is that if the energy of absorbed light is sufficient, which is greater than the band gap of the bulk semiconductor, excitation happens. The electron in the valence band excited to the conduction band. Will that be the only excitation? No, the answer is no. We could have so many excitation, for example, to the higher energy levels, and higher, and so on and so forth. So these are the excitations that could happen in the bulk semiconductor. Could someone please open the door for our friend? Now, this excitation will be detected. The light that is being absorbed, for example, the excitation number 1 over here, the light that is being absorbed is different from the second excitation, third, fourth, and fifth, so on and so forth. Different light will be absorbed depending on how high is the electron will be excited. So this will form very broad and indistinct peak of absorbance spectrum. The absorption spectrometer will give you the output in the form of graph, and the graph will be very broad and indistinct peak. For example, this is the graph. We have x-axis, which is the wavelength of light that is being absorbed, the wavelength of this light, and this is the absorbance. How intense the light is that is being absorbed. For example, for excitation number 1, which light is being absorbed? For example, maybe could be 1400. And how intense the light of 1400 nanometer will be absorbed. So cumulatively, if we combine all of the excitation, we got very broad peak. For example, excitation number 1 over here, again, this is excitation number 1, it will give you this peak. And how about the second excitation? This is the second excitation, it will give us this peak. The next excitation, the next graph will be like this, so on and so forth. And cumulatively, the machine, the instrument, will give us only one graph, cumulative graph, which is the red line over here. It won't give us the blue lines. No, it doesn't. It will give us only the red graph, which is cumulative of all the excitations. So you will get very broad and indistinct peak. We could just only guess. Maybe this is the peak. Guess. which is could be true, could be wrong. It is very broad and indistinct. We cannot see clearly which one is the peak. This could be the peak. Maybe there is hidden peak somewhere over here, or somehow maybe there are also peaks over here. So it is indistinct because the peak is very broad. So how do we differentiate? How do we determine which position is the correct first excitonic peak? We want the first excitonic peak. We want the peak from this excitation. So, how do we determine? We need to determine the top or the peak of the graph. This one indicates the light that is being absorbed. The first light, the longest wavelength of light that could be absorbed by our semiconductor. And this side of graph could be reflected, and this side of graph indicates the transmitted light. This is in the case of bulk semiconductor. We will get very broad peak. However, in quantum dot semiconductor, because we have different form of band, we don't call this as band. We call as energy levels. This one is HOMO, and the yellow one is HOMO. This is HOMO. This is LUMO. LUMO 0, LUMO plus 1, LUMO plus 2. HOMO 0, HOMO negative 1, HOMO negative 2. And they are well separated. We could distinguish between the energy levels. We could differentiate between the first, second, and third energy levels, so on and so forth, including the HOMO and also the HOMO. We could differentiate between the energy levels. So how about if we try to expose our quantum dot semiconductor under illumination of sunlight? Let's see. So basically, the conduction band is made of widely separated energy levels known as unoccupied molecular orbitals. And the electron excitations occur from the valence band to each corresponding energy levels in the valence band. Again, this is typo. This is conduction band. Actually, we don't call it this conduction band. We call this HOMO. This one is HOMO. This one is HOMO. Same goes for this one. This is HOMO. Right. So excitation happened. First excitation, second excitation, third excitation. Very limited number of excitation could happen in quantum dot semiconductor, unlike the bulk semiconductor. The bulk semiconductor could have unlimited excitations because we have so many energy levels separated closely to each other. But this one, in quantum dot semiconductor, the energy levels are well separated, widely separated, and we could have only limited number of excitation. The highest number of excitation in quantum dots, the maximum could be 4. Usually 4. Okay, this is first, second, third, and we could have one more excitation over here, goes to the LUMO 3. So what happened to our graph? So it will form very narrow and sharp peak of absorbance spectra, for example, like this. First excitation will form one graph, second, this graph, and third, this graph, and cumulatively, we could get this graph. And it is clearly, we could observe that this is the first peak. This is the first excitonic peak, which correlated to the first excitation over here. First excitation is very useful information for us to determine the band gap and also the responsiveness of our semiconducting material with the exposed light. We need this information. This information of first excitation is very crucial. That's why it is important. So this one is clear. This is the first excitonic peak. Otherwise, this one in the bulk semiconductor, the peak will not be clear. These are the differences. So today we will learn how to modify the graph, how to do fittings using microcal origin, which I believe I have distributed the software of origin for you just now. So some of the computer which is running on Windows 10, unfortunately you cannot use that software. If you have Windows lower than Windows 10, for example Windows 8 or Windows 7, so you could use that software. So you should find other version of origin. You could buy or you could find from the internet, or you could borrow from your friends. So before that, let us see the main components of an absorption spectra. Of course, the most important thing in absorption spectra is the lamp. The lamp which gives you the light spectrum, the desired light spectrum. So usually we will have three regions of spectra. The first region, which is the ultraviolet, we need to use deuterium lamp, D2 lamp, deuterium lamp, and we need one more type of lamp, which is tungsten lamp, which could produce light in the visible range from red until the violet, and also we need the near infrared, which also could be produced by the tungsten lamp. So usually we need to use a combination of two lamps, and it can be switched automatically by the instrument. We don't need to switch them manually. And of course, we will have filter to filter out any noises, any unwanted spectra. Sometimes it produces spectra more than ultraviolet C. So we need to filter them out so that all the light over here will be purely from the visible until near infrared, from 200 until 1400 or 3300 nanometer, depending on the machine. So this is the monochromator, and the function of monochromator is that to select which light should be exposed to the sample one by one. For example, our graph over here, we need to start analyzing our sample using the first using the first wavelength, which is 200. So we need to shine our sample with light with 2200 nanometer of wavelength only. So we need to filter the light. This light contains so many wavelengths from 200 to 1400. So the function of monochromator to filter out which light should pass through the monochromator and beam splitter to the sample. If we want to plot a graph which corresponds to x equals to 200 nanometer, we should pass the 200 nanometer of light and goes to the sample and go to the photoray, which is the sensor, and produce the graph. One plot 200 nanometer should get one plot over here, 1 point. Then it goes to the second round. After 200 nanometer, the monochromator select 201 nanometer to pass through the monochromator to the beam splitter to the sample, and then the sensor of the machine will detect the intensity of absorbed light and plot the second graph. 201 goes on and so on and so forth for 202 until 1400 nanometer. So the machine automatically detect and record the data for you. And this is the reference, the blank sample, which contains only the solution for your semiconductor material. This method is used not for thin film, for if you suspend your semiconductor material inside the solution. So if you suspend your semiconductor inside the solution, the reference should be blank sample, for example ethanol or water, and your sample should contain the semiconductor plus the solvent. This is blank solvent, this is your sample, and this is the graph. So again, these are the functions of each of the component in the absorption spectrometer, which I believe I have explained just now: deuterium lamp, tungsten, and also we could also choose xenon lamp depending on the maker of the absorption spectrum. So xenon lamp also produces from ultraviolet to visible light, tungsten from visible light to near infrared, deuterium only visible light. Monochromator, it acted like filter of the light, sample compartment to place our samples, detector to detect the absorbed light, the transmitted light, and also the reflected light. These are the main components of absorption spectra. 4 main components. The others, they are just accessories. So, how do we assign proper excitonic peaks in our graphs? So, which peak belongs exactly to which wavelength? So, the tool that we need is microcal origin, the version that is compatible to your laptop or your PC. The one that I gave to you is only compatible up to Windows 8 only, unfortunately. If you brought your own laptop, if it is running in Windows 8 or lower, then that software could be used. Unlike our new PC over here, they have been installed with Windows 10. Unfortunately, we cannot use them. So how many of you got Windows 8 and below? Siapa punya laptop ada? Ada buat? Good. Ini Windows 10, 10, 10, 10, 10. 8. Can open, really? Alright, anyway, let me stop the recording for a while. Let's try to troubleshoot your laptop. So, you need to open your Origin Pro icon and click your Origin Pro icon and Control O, which is File, Open, and select the folder Origin Pro 8.6 Portable. Open the case study file, the case study.opj. Open that file. So you have you opened that? Okay. Now this will be your interface. You will have the X, Y, Y, so many Y's, and please for the time being highlight AX and BY only. Highlight these two columns only, AX and BY. Done? Done? Okay. And click the line plot as indicated by the red circle over here. Click this button, the line plot. Got that? Done? So you will get this kind of graph, kan? Yes. Can you tell which where is the position of the peak? Cannot see the peak at all. So this is an example of absorption spectra of a bulk semiconductor. We cannot see the peak clearly. So what you need to do is that now click analysis, click the analysis tab, hover on the peaks and baseline, and hover your mouse at the multiple peak fit and click open dialog. Analysis, peaks and baseline, multiple peak fit, and click open dialog. This one, open dialog. Analysis, peaks and baseline, multiple peak fit, click open dialog. Ada? So next thing is there will be a pop-up. Okay, this pop-up you need to click at the peak function, choose Gaussian. Not Gauss, but Gaussian. From the drop-down menu, choose Gaussian and click OK. Done? Done? Next, another pop-up will be shown. So your strategy is that we will try to fit 4 excitation curves in the given graphs. Remember, we could have multiple peak, multiple absorption spectra in this cumulative spectra. So we will try to fit 4 excitation curves only. 4. So double click at a spot in the graph to assign a peak of an excitation curve. Choose a point that might have a peak. Just take a wild guess. If you could see over here, maybe there is a peak over here. Click, double click in this spot, and if you look at this region, there could be another peak. Double click at this spot. Do it for 4 spots. Choose 4 spots. Double click at each spot. Done? Double click at each spot. Double click. Choose 4 spots. Got that? So usually a red line will be shown after you have clicked at the corresponding point on the graph. Every time you double click, there will be a vertical red line. So these are the points that might have hidden excitation peaks. So now, click open NL fit over here. NL fit, there will be a pop-up with get points and click open NL fit. Done? Okay. Another pop-up will be shown. And in this pop-up, click bounce tab. Bounce, this one. This is the pop-up. Choose bounce tab. By default, the pop-up will show you the parameter tab, but do not use that tab. Click bounce tab. Done? Next. So after you click the bounce tab, these are the parameters that you need to optimize. So this is how the bounce tab should be look like. We will set the maximum and or minimum value of our fitting. We need to set the minimum and maximum. So how do we set them? First, change the setting of the less or equals to tab of the upper bound. This one. This is upper bound, this is lower bound. So we need to change this one first. Refer to the red circle and the red boxes. Double click the box here, the FWHM. This one is for FWHM. Double click this field until this symbol comes out. Each and every FWHM. Look for FWHM. Double click at the blank space until it shows less than equals to. FWHM stands for full width half maximum. For example, if your peak is like this, FWHM is this one. Let's say this is the peak and the peak is 100, so you should choose this one, 50, and this is the full width half maximum. The full width of the half of the maximum of intensity. This is the full intensity. This is half maximum of intensity. So what is the width of the half intensity? This is the width. The full width of the half intensity. Full width of the half maximum intensity of the graph. So we set, usually we will set the FWHM equals or smaller than 100. So put the value 100 here in the upper bound. It could be other figure. We try with 100 first. Let's see whether we could get the fitting correctly. So if you have finished that, continue with the lower bound. Lower bound must be on 0, except for base. Make sure the base one is left untouched. Do not fill in anything in the space for the base. So the lower bound should all be 0, and this side should be smaller than. Yeah? Can I read it? Can we check? Next, click simplex button, the one with S. Many times. Click simplex button many times. As many as you want. Until you get sort of like this graph. Did you get this graph? Until the 4 excitation curve, the green, blue, light blue and red line, for example, in this graph, the color of your graph might be different from the PowerPoint slide. So until the 4 graphs plotted in the form of Gaussian type are shown. So usually the purple graph, you could see the black, the original graph is in black, and the purple graph. So, if your purple graph coincides perfectly with the black graph, it means that your fitting is perfect. For example, like this graph, you could see that the black and the purple lines are not coincide. So the fitting is not perfect yet. So we need to fine tune. So how do we fine tune? So look at point number 2, fine tune is needed from the individual excitation curve. You can see that there is a missing curve at 650 nanometer over here. This one, maybe they differ only little. But however, at 650, you could see that the difference between the purple and the black lines could be observed. So we need to fine tune at this point. So from my case, this is my case. I don't know what about yours. Similar? Similar? Are they similar? No. If not similar, I have to look one by one. So example like this, you could observe that the purple and the black graph doesn't coincide very much over here. Something is missing. So what you need to do is that there is a missing curve at 650, as you can see. Read from the center. The first peak center is 533. 533 is this one. Yes, we have one 533, the red graph. Second one, second graph. Center is 337. 337 over here. Oh, okay, we have the green one somewhere over here, even though the graph is cut. Okay, it's not shown. The full graph is not shown because our data is only started from 350. Doesn't matter. Leave it that. Graph number 3. Center is 134. 134. Somewhere over here. Look at your data. Your data starts from what is the lowest wavelength of your data? Berapa? Look at the table of your data. What is the shortest wavelength? This one. 350 kan? This one. Your data starts from 350 nanometer, which means that if your plot shows something which is smaller than your first point, this is wrong. Never mind, keep in mind that this is wrong. Look at fourth graph, center is 436. 436 somewhere over here. Yes, we have the light blue color. So the one that is wrong and need to be modified is this point, which is out of our data. Not even in our data. Our data starts at 350, but it shows 134, which is wrong. So this one should be replaced by this one. Understand? Okay, first look at the fitted graph and the original graph. The original graph is black color, the fitted graph is purple color. Find a region where they doesn't coincide. They doesn't coincide here, but very small differences. Okay, negotiable. Until this point, they differ greatly. The difference could be observed. They doesn't coincide. So our hypothesis is that there should be a peak over here, one missing peak, which is not fitted in our calculation. So now our next task is to analyze one by one of the fitted graph. Which one is the bogus one? Is the fake peak? How about the first 533? 533, yes, over here could be a graph over here, could be a peak. 337 somewhere over here. The green one, yes, could be a graph over here. 134, this is bogus. 134 is not true. This is fake. Because our data starts from 350 and this one starts from 134, which is fake. Okay? KIV. Proceed with fourth graph. 436. 436, yes. This one, we could have this graph. So the one that is missing over here is actually this one. This one is not 134. This one need to be modified, becomes 650. Understand? Boleh? So if we put a peak over here, definitely the purple graph will be shifted upward and coincide with the black color. With the black graph. If we put a peak over here, the purple line will be shifted upward, and somehow it could be coincide with the black graph. Understand? So what you need to do is that adjust the value of the center over here. Okay. Oh, I have explained just now how to analyze one by one. Okay. Change the center of 134 becomes 650. 650. Because there is a loop over the missing graph at 650. 650 or somewhere around that area. 640 or 630. Yeah? And click simplex button again, repeatedly. And let's see your next graph. Done? Change 134 becomes 650 and click simplex button many times until you see Gaussian graph again. So now how about your fitting? Still similar or change? Change. Does the purple graph and black graph coincide at 650? Yes. Coincide? Let me check. And I have checked your graph. Looks like okay. Okay, imagine that if you got this kind of graph, even though the center already being modified 650, this one still 436, 337, 533, which could be legislated to true. Okay, they are all in the region of the data. But how about if the center are correct? However, the graph, the purple graph and the black graph still doesn't coincide over here. So next stage, what you need to do is that look at the amplitude. See this one? The amplitude is 10 to the power of -12, which is very, very small, super small. And you need to modify this, increase it, becomes 80 or 60 or 20. But your graphs are okay. Do not modify your graph. They are okay already. So if the center, if it happens later, if you try to with another data, if the center are correct, but you still cannot see any. See, it has 650. There should be one peak over here, but it doesn't show any peak at all. So it happens because your amplitude is too small. Change it to 20 or 60 or 40, then you will see another Gaussian graph will appear over here. So let's say I modify this one. Okay, modify that one. I put 12 for example, and click simplex button, then I will get this kind of graph. See how the purple and the black lines now coincide. So this fitting is acceptable. If your fitting, you have satisfied with the fitting, click this button. Fit until converge, this button. Done? Done? Converge tak? Convergence fail. Fail. So what you need to do is that click simplex button again and fit until converge. Simplex many times, fit until converge, until your fitting converge. Converge. If converge, successful lah, and don't click anything yet. Okay, how do we read the fitting? First, remember we have few excitonic peaks. This is the first excitonic peak. Choose the peak, the one that indicated with XC. Choose XC with the longest wavelength. You should have 4 XCs. Choose the axis with the longest wavelength. And let me know the value. 5? 591 point? Nearly similar to mine. How about yours?
591.78864.
Yes. nearly similar to mine. So the first peak, we have concluded that my fitting and yours nearly similar, 591.7 something. So that peak is acceptable. So this is your first excitonic peak, which is correspond to this excitation, the first excitation. So how about the second, third and fourth? Second, choose the XC with the second longest wavelength, which mine is this one. Mine is 500.4 something. Same? So that is the second excitonic peak, which belongs to this Gaussian peak. This is the first, see, this is the first excitonic peak, which is non-observable previously. Now it is observed clearly with our fitting. Second excitonic peak. Third excitonic peak, XC is 418.5 something. 418.5 something. Sama? Same? Similar. And fourth excitonic peak is this one, 325.7 something. Same? Yes. So it indicates that our fitting is correct, acceptable. So this is how you do a fitting for any absorption spectra. Make sure you do fitting at least 3 times and compare whether the value will be similar or not. If the value is similar, then your value is acceptable. So this is how you do fitting, not necessarily for absorption spectra. You could do this fitting for XRD as well, FTIR, what else? Any spectra, any machine that gives you X and Y axis graph could use the fitting. So you still have more data sets, right? Try give to other members to try with the different data set. We have set 2 until set 7. Ada banyak di set. Try the sets. Try different set. Highlight AX. AX is a must. Second set, you have to highlight AX and CY. Third set, AX and DY, so on and so on. So good luck doing the fitting.